Greetings, Panthers. It's Dr. Augustine again. Today we have a very important concept we're going to talk about. We're going to talk about the mole concept, which is really probably one of arguably the most important major concepts you can learn in Gen Chem 1. And we're also going to see how that relates to molar mass, or the term called molar mass, and then this number that you've probably heard of called Avogadro's number, where that comes from. So no chemistry video about moles is complete without some cheesy mole pictures. These are from the American Chemical Society. You can Google chemistry moles and you get all kinds of pictures like this. This is little child mole called Avi. This is Dr. Erlenmeyer, and this is Professor Molnium. And if you want to find out more about these little mole friends, you can go to the American Chemical Society, acs.org, outreach moles, and you can find many, many more pictures of our chemistry mole friends. So as you probably know, 10/23, October 23rd, special day for chemists, is National Mole Day, 10/23. And you also know that weird number 6.022 times 10 to the 23rd. So the point of this video is going to be we're going to cover section 2.9 intro, molar mass, counting atoms by weighing them. And the major topics are: what is a mole? Why this weird number, 6.022 times 10 to the 23rd? Converting between moles and atoms, and just general big picture, the mole concept, also known as the chemist's dozen. So let's start with the periodic table again, and let's look at some of these numbers on the periodic table. And I want you to follow along with the logic, because if you remember from the last video, we said that the average mass of a carbon is 12.01 a.m.u. And you remember the other thing we said is there's no such thing as an atom that has a mass of 12.01 a.m.u. It's either carbon 12, which is 12.00, or it's carbon 13, which is approximately 13.00. These are a.m.u.s. Okay, so if we were to pick up individual atoms and measure them, we would find, and I could put more zeros on this one, I know exactly what that one is. Every time we found a carbon 12, remember that's almost 99% of the carbons that we found, they would be 12.000 a.m.u.s. And every time we found a carbon 13, which would only be like 1 in 100, it would be 13.00 something something a.m.u.s. Okay, be a little bit heavier than the carbon 12s. So that's measuring individual atoms, but you might be thinking to yourself, well, how am I going to possibly measure an individual atom? Even if I had my fancy scanning tunneling microscope, it makes it look easy because the images look pretty good, but it is not easy to look at individual atoms. And with a mass spectrometer, we're really looking at bunches of atoms going into the mass spectrometer, so we're not looking at an individual atom. So what we're really interested in is, how can we measure like real quantity scales of things, like maybe something that would show up in a test tube like this, or in an Erlenmeyer flask, or in a beaker? How can we measure real world quantities of these things, and what term can we use? We don't use atomic mass units when we measure real world quantities. We do things in grams. So I want you to follow the logic here, because if you follow the logic, you're going to understand how the entire periodic table sort of falls out. Okay, so actually I'm going to make this a little bit bigger so you can see it. So here's the periodic table, and we've got all these different elements on it. We've got carbon, which is 12.01 a.m.u.s, and we got something like helium, which is 4.00 a.m.u.s. So would you agree with me that helium and carbon, okay, and I should put the units on these just to be consistent and for good practice. So if we were out in nature and we're looking at elements, and we were able to find individual atoms and somehow able to measure them, we would find that every time we found a carbon atom, it would weigh 3 times more than every time we would find a helium atom. And if we found a hydrogen atom, it would weigh 12 times more. So carbon's 12.01, hydrogen's 1.01. So carbon is 12 times heavier than hydrogen. So I'll write this one down just for the sake of argument. So hydrogen is 1.01 a.m.u.s. Okay, so does this make sense? If we're hunting around in nature, we find individual atoms and then we compare them, they would always be in the same ratio that's on this periodic table. Hydrogen, 12 times lighter than carbon. Helium, 3 times lighter than carbon. If we looked at something that was like 24, let's find one of magnesium. Magnesium is about twice as heavy as carbon is. Okay, and the example you might use, just sort of give you a sort of an illustration of this, this might be like, hydrogen might be like a ping pong ball or something. And this might be like a tennis ball. And this might be like, I don't know, a lacrosse ball or something. This analogy isn't perfect because the sizes aren't quite right, but you get the idea that one is lighter than the other is lighter than the other. And if you compared them, if you started finding more and more of them, they'd always be in the exact same ratio. Okay, it's always 3x here, it's always 12x here. Magnesium is always twice as heavy as carbon every time we found one of those. Okay, now follow along with the logic and hopefully this periodic table will make sense. All right, so suppose we had, suppose we found 100 carbon atoms and we found 100 helium atoms and 100 hydrogen atoms. How would the ratio then compare? So we bump this up to 100, 100, 100. This is now 1200, this is 400, and this is 100. But guess what? The mass ratio is still exactly the same. 100 hydrogen atoms is still 12 times lighter than 100 carbon atoms. 100 helium atoms is still 3 times lighter than 100 carbon atoms. And if we had 100 magnesium atoms, it would still be twice as heavy as the 100 carbon atoms. All right? Well, what if we went to 10,000 hydrogens, 10,000 heliums, and 10,000 carbons? They'd still be in the exact same ratio. What if we went to 1,000,000 hydrogens, 1,000,000 heliums, and 1,000,000 carbons? They would still be in the exact same ratio. What if we went to, I don't know, just kind of coming up with a crazy number. What if we happen to have 6.022 times 10 to the 23 hydrogen atoms, helium atoms, and carbon atoms? I've just picked some crazy number out. Well, it turns out they would still be in a 1 to 12 ratio between hydrogen and carbon. Helium and carbon would still be in a 3 times lighter, and carbon would still be 2 times lighter than magnesium if we happen to have 6.022 times 10 to the 23rd of these. So this magic number, as I'm sure you're all aware, is called Avogadro's number. But that still doesn't answer the question, why this crazy number? Why 6.02 times 10 to the 23rd? Why is all of chemistry based on this ridiculous number? Couldn't you have made it easier on us? Couldn't you have just said this is 1.00 times 10 to the 10 or something? I mean, if you wanted to just pick some big number, couldn't you just pick some even number instead of this 6.022 times 10 to the 23rd? Aha, well, it turns out that if we were to measure the same mass of carbon-12, so we're going to go back to carbon-12 as our standard. If we were to measure 12.000 all the way out to infinity grams of carbon-12, it just so happens to have 6.022 times 10 to the 23 carbon-12 atoms. Okay, so we're still using carbon-12 as our basis, and if we take the mass, instead of in a.m.u.s, if we take the mass in grams, 12.000 grams, and we were to somehow count out all the atoms, it would have 6.022 times 10 to the 23rd carbon atoms. So what that means is, if we convert the a.m.u.s, or if we switch units from a.m.u.s, which is a unit, a very small unit of mass, and we switch it to grams, which is something we can actually measure in the lab, then whatever the mass is in a.m.u.s in grams, that happens to have 6.022 times 10 to the 23rd atoms. Okay? So it's still 3 times lighter for helium, but there's 6.022 times 10 to the 23rd helium atoms in 4 grams of helium. In 1.01 grams of hydrogen, there are 6.022 times 10 to the 23rd. And in 12.01 grams of carbon, there is 6.022 times 10 to the 23rd atoms. Just going to give you one thing of notation. Sometimes Avogadro's number is given the symbol capital N, small a. No, it's actually a capital A, but a subscript. Okay, so that's the notation sometimes used for Avogadro's number. All right, so this is a really special number. It turns out that that mass, if we measure that in grams, it's any one of these masses on the periodic table, if we measure that in grams, it has 6.022 times 10 to the 23rd atoms. So why is this a big deal? I mean, why do we go to all this trouble of this Avogadro's number and 6.02 times 10 to the 23rd? Well, it turns out that's a measurable amount of stuff. Okay, measuring one atom is not realistic. Even with a really good mass spectrometer, even with a really good scanning tunneling microscope, measuring things one atom at a time is not a realistic thing to do. But we do measure realistic quantities of things in the lab, things that'll fit in a beaker, things that'll fit in a graduated cylinder. So we need a mass unit that's much more convenient than an atomic mass unit, and grams is a much more convenient unit, but we also want to be able to measure sort of normal quantities of stuff. Turns out that the mass of copper is 63.55 grams copper for every 1 mole of copper. Now look, if you know something about pennies, you know, well, that's not all copper. There's really zinc inside of there. Okay, fine. Pretend these are all copper. So that mass, about 63.55 grams of copper, is 1 mole of copper. We can also look at molecules. So we can take something like water, which is not it's not an atom, it's a molecule, it's H2O. And we can take a mass of 1 mole of water is actually 18.01 grams H2O for every 1 mole of water. These quantities that we're describing right now are called the molar mass. Actually called the molecular mass for molecules and the molar mass for an atom. Okay, so molar mass is the term of atoms, and molecular mass is the term for molecules. It's the same idea though. It's the sum of all the atoms that gives you 1 mole of stuff, and it's the mass that you can measure. And these are measurable quantities. Like, I mean, that's a reasonable amount of stuff to have. This is a reasonable amount of copper. If you had a mole of each of the elements, you could see how the sizes vary as you go down the periodic table because the elements get heavier and heavier and heavier. So you can see there's a lot more copper than there is water because water is made up of light molecules, hydrogen and oxygen, whereas copper is a heavier material. So before we go on to doing a couple sample problems, let me give you a sense for why this is so important. And sometimes the mole is called the chemist's dozen. And let me illustrate what they're talking about. When you hear this term chemist's dozen, what does that mean? Well, we have other units that we use to group large numbers of things, or maybe not even large numbers, just groupings of things. So for instance, we have a word called a pair. Have a pair of shoes. Well, what does a pair mean? Pair means 2. We have a thing called a dozen. What does a dozen mean? A dozen means 12. What if I have 5 dozen or 2 dozen? 2 dozens 24, 3 dozens 36. So I can have more than 1 dozen. Half a dozen means 6. But when I say the word dozen, you understand I'm talking about 12. So if I say I have half a dozen, well, that's half of 12. We can have things, something like a gross, 144. We have another term called a case. Case of your favorite beverage comes in packages of 24. Okay, so we have ways to group large numbers of things. We have terms used to group them. So whenever we have a large group of things, like on the scale of say 12 or something, we might call it a dozen, or a scale of 24, we might call it a case. What if we have a large number of things like, oh, I don't know, 6.022 times 10 to the 23rd. So 6.2 times 2 times 10 to the 23rd, we have a new term we call a mole. Okay, and a mole could be any object that is 6.22 times 10 to the 23rd. So one of the sources, I think, of difficulty with this term, is many students, when they hear the word mole, automatically think atoms. Okay, and it's not necessarily atoms. And you could have a mole of anything. You could have a mole of toothbrushes. That would be a lot of toothbrushes. You could have a mole of pennies. That would be a lot of money. You could have a mole of sand, grains of sand on the beach. That would be, I don't know, that would probably be a lot of sand also. And you could have half of a mole. That'd be 3 times 10 to the 23. You could have 2 moles. That'd be 1.2 times 10 to the 24. I'm doing ones I can do in my head fairly quickly. But my point is, you don't just have to have 1 mole. You can have a half a mole, you could have a quarter mole, you could have 0.1 moles, you could have 7 moles. So mole just means this number, 6.022 times 10 to the 23rd, modified by whatever we're interested in, 5 moles, a half a mole, 10 moles, something like that. Okay? So to the chemist, when we hear the word mole, our brain is thinking 6.022 times 10 to the 23rd. Now, depending on what the actual problem is, will depend on the context, and that will depend on how we would approach that problem. So let's take a look at 2 different types of problems. These are 2 kind of classic problems, and let's take a look at how we would solve these. We're going to start with this one here. How many moles of nickel are in 225.7 grams of nickel? So if you want to stop the video here and think about it, we can, I'm going to clean up this screen and then we'll come back and solve this problem. So the way we approach this problem is we need to know what the molar mass of nickel is. I've already looked it up. Nickel happens to be 58.69 grams of nickel for every 1 mole of nickel. Where did I get this number from? This came off the periodic table. Okay, that's the number next to nickel on the periodic table. So I want to know how many moles of nickel are there in so many grams. So this could be any arbitrary number. I'm just going to write this problem out this way. How many moles? And the shorthand for mole is MOL instead of MOLE, which doesn't really save that much space. We start with our number that could change. It could be any arbitrary number. 225.7 grams of nickel. I want to get rid of grams, so I'm going to put a conversion factor in here. I want grams nickel on the bottom, and I want moles nickel on top. And that, therefore, this is going to be 1 mole of nickel for every 58.69 grams of nickel. That cancels that, and my answer is 3.845 moles of nickel. Now we want to check our sig figs just to make sure we're right. We've got 4 sig figs here. We've got 4 sig figs here. This is infinite, 1.000 moles for every 58.69 grams. So I should have 4 sig figs here. And my answer then is 3.845. Now, does this make sense? Well, yeah, because a mole is like about 60 grams, and this is almost 4 moles because this is 225 grams. So we have more grams than a mole, so it makes sense that we'd have more than 1 mole. So we have 3.845 moles of nickel. And the next question, which is a pretty common type question, is how many phosphorus atoms are in 15.5 grams of phosphorus? So when you see one of these problems, if the number is asking for how many moles, like how many moles, and you're starting with grams, you should be thinking, I need molar mass to do that conversion. So in the prior problem, it says how many moles are in so many grams. Your brain should be thinking, I'm going to need to know the molar mass. But the second problem is how many phosphorus atoms are in kind of a normal amount of stuff, 15 grams. This is going to be a huge number. Like that, when it says how many phosphorus atoms, that should tell you it's going to be a whole lot of atoms. Because remember how many atoms are in this bit of copper from up above? 6.022 times 10 to the 23rd. If you have a measurable amount of stuff, you're going to end up with a large number of atoms. So if I've got 15 grams of stuff, which is a measurable amount of stuff, I'm going to end up with a large number. If you have a large number, you should expect Avogadro's number to show up in your calculation. So if you want to stop the video and see if you can calculate it, and we'll come back and solve this in a second. Okay, so let's take a stab at this one. How many phosphorus atoms in 15.5 grams of phosphorus? This is my number that changes. We always start with my number that's changing. This could be anything. I can make up any number for this, 75, 15.78, but the rest of it's not going to change. So I'm going to say how many phosphorus atoms. That's what I'm trying to shoot for. And I'm going to start with my number that can change, 15.5 grams phosphorus. Now, I can't go directly from grams to atoms because each atom has a different mass, but I need the molar mass in order to do that. I've looked this up on the periodic table, 30.97 grams of phosphorus for every 1 mole of phosphorus. So I want to put the mass on the bottom, right? Grams phosphorus on the bottom, mole phosphorus on top. So I've got 30.97 grams of phosphorus for every 1 mole of phosphorus. Grams phosphorus cancels gram phosphorus. If I was trying to find moles, I'd now have it. Kind of like the last problem was just trying to find moles. But now I want to find atoms. So now I need, for every 1 mole of phosphorus, there is I'm just going to cheat and use this, 6.022 times 10 to the 23rd phosphorus atoms. So moles of phosphorus is going to cancel moles of phosphorus. How do I know this? Because the definition of a mole is 6.022 times 10 to the 23rd. Just like the definition of a dozen is 12, definition of a case is 24. 1 mole is 6.022 times 10 to the 23rd, whatevers, and in this case we're looking at phosphorus atoms. So all these units are going to cancel, we're going to be left with phosphorus atoms. So when we do this calculation, this equals to 3.013 times 10 to the plus 23 phosphorus atoms. And using rules of sig figs, this has 3 sig figs, this has 4 sig figs, this one has 4 sig figs, so my answer should have 3 sig figs. So I'm going to need to round this place right here. So this is going to equal to 3.01 times 10 to the 23 phosphorus atoms. And if you look at this closely, 3.01 is about half of 6.02. In fact, it's almost exactly half, which makes sense because 31 grams of phosphorus is in a mole, and we've got 15 and a half. 15 and a half times 2 is 31. So we have almost exactly 1/2 of a mole because we're starting with 15.5 grams. Okay, this could have been any number, but it happens to be 15.5. So we end up with something that's 1/2 of a mole of phosphorus atoms, but the actual number of atoms is 3.01 times 10 to the 23rd. Okay, you're going to have plenty of time to practice doing these calculations, but this hopefully gives you a sense of the importance of this chemist's dozen. This number we call a mole is equal to Avogadro's number.